Hello Year Sixers and welcome to today's science lesson. Last week we were learning about particles in solids, liquids and gases and how they change from one state of matter to another state of matter. This week we're thinking about how we heat particles and exactly what's happening within our solids, liquids and gases. Let's start with some retrieval practice about our solids and liquids and gases and their particles. We've got some true or false questions. Make sure you've got your pen or pencil to write down true or false for each of these statements. The particles in liquids are stuck together in a rigid structure. So in a liquid, the particles stay together in a rigid structure. They do not move around one another. That is false. Well done if you've written down false. In a liquid, although they may be touching, the particles run around each other, they move around each other, they slide past each other, bumping into each other and going around one another. It's in a solid that they make a solid structure, a rigid structure, as in the picture above. The particles in a gas are free to move around. Is that true or false? It is true. If you look at our picture, the gas particles are flying around, and gas particles fly around the room all of the time. They bump into each other sometimes, they go around one another, but they fill the space, they escape through small gaps, they are everywhere. Generally, a solid keeps its shape, so most solids, whatever shape or form they're in, they will keep that shape unless they are pressed or pushed. That is true. It's a true statement. I wrote the word generally there so you didn't get too confused. When you think about sand, sometimes you think about it changing shape, or it can be poured, for example. However, each individual grain of sand is solid. It keeps its shape. The next one, a liquid keeps its shape. True or false? A liquid keeps its shape. That one's false. A liquid will fill the container, or the bottom of the container that it's put in. So if you poured it from a tall glass to a shorter cup, it would fill the space at the bottom of those that cup or that glass. Or if it was left on the floor, it would make a puddle, it would spread out. And finally, a gas fills the space it is given. So will a gas fill the space it's given? True or false? That's a true statement. Gas will fly around, filling as much space as it possibly can, full of energy and getting as far apart as it possibly can. Okay, so let's just recap these. We've got melting here. We've got our solid structure, and then the particles turn into a liquid as they melt. So they go from a rigid structure to a structure where they can move around one another and slide over one another. This only happens when the solid has heat applied. Now, I'll put a flame here. It doesn't always have to look like a flame. Sometimes it's just heat from your hand if it's snow melting in your hands, or it could just be heat from the wall, from the room that something's in, the solid's in. Okay, so it doesn't have to be a flame, but it does. I've used a flame to represent here that it's heated up. So if you imagine all of these particles are rigidly stuck together in a formation, but they've still got some energy and they tend to vibrate against one another. And the more heat they're given, the more energy they're given from the heat source, the more they vibrate. And eventually they vibrate so much that they fly apart from each other and begin to slide over one another, which is why when you've got an ice cube, it tends to melt from the outside first. That's the bit that's getting the heat energy the most. So that's the bit where the particles will start to slide over one another and form a liquid. Okay, so these particles, there's sort of a little bit of give and take in them. They've got different amounts of energy. So a piece of ice that is frozen for a long time at a really low temperature, the particles are almost still, the vibrating is very small. However, just before it melts, just before the particles actually move apart and slide over each other, they're vibrating quite a lot. They've got quite a lot of energy in them to release themselves from that rigid bond. If we look at this evaporating, we've got here the liquid turning into a gas. Now, these liquid particles have got a fair amount of energy, got enough energy to be sliding over one another. Not so much that they're moving apart, but they've got enough that they're sliding over each other. So again, when heat is applied, it doesn't have to be literally a flame, but when heat is applied, it gives them even more energy, and they start sliding over each other faster and faster until eventually they can free from each other, they can fly apart from each other, and then they escape as a gas form. And they're released from their bonds altogether. This is the other way around. So this is condensing. This is when we go from a gas, the particles flying around the room, to a liquid, and that happens with condensation on your windows. Sometimes there's a lot of water vapor in the air, and it will go to a cold window where it will come together. So this is the absence of heat. This is where there is less heat. There's less energy. The heat gives off an energy, where if there's less energy, then the particles are given less energy, and as they have less energy, they end up coming together and joining together. There's not enough vibration, if you like, to keep them apart from each other. So where they're cold at the window, where there's a lack of heat at the window, they'll form water again, if it's or a liquid again. Okay, so the lack of heat forces the gas to come together. Okay. And then we've got freezing. This is when you've got a liquid and it turns into a solid. Again, once this liquid is really, really cool, there's no heat getting to this liquid, the particles slow right down. So they were moving across each other, moving around each other happily, flowing around each other as a liquid. But as they don't have enough energy to continue to do that, they then start to form a solid. And you've got a picture just behind my face, and that's of an ice crystal forming. And this forms slowly as the water particles slowly stop sliding over one another and start to form a rigid pattern. Okay, so that's the freezing process. But if you think about it more as a sliding scale, so some things can be frozen solid where some are on the brink of almost melting, and that shows you kind of how much energy each of these particles have got. They don't go from being a solid where they are absolutely still to a liquid where they've got a little bit of energy. They're like at walking pace, and then they're at a flying around pace of running when they get to a gas. Instead of that, you can think about it more as if you were running a race. You speed up or you slow down over time. Okay, and it's about how much energy you have. And for our particles, that depends on how much heat they have going to them. So we're going to look at the word expanding here as our key vocabulary today, and we're going to be thinking about solids expanding, particularly in these photographs, metal expanding, because metal's a good example of this. And most metals around us are in a solid form. You rarely see a liquid metal around us, although our next slide does look at that. So the metal here is the metal on train tracks. Now the metal on the train tracks should be parallel. They should be exactly the same width apart, and train tracks are built to be as straight as possible, and they're fixed really tightly to the ground with big wooden structures. Okay, railway sleepers, they're called, those big wooden blocks that they're nailed to. Now it's really important for these to be dead straight and parallel so that the train stays on the track. However, with expansion, sometimes they end up with kinks in them, wobbles in them. What happens is the sun heats the metal, and as the sun heats the metal up, all of the particles start to jostle around, they start to move. They don't quite melt, they're not melting here, but they're doing something called expanding. So the structure is getting bigger and bigger, and actually the metal itself is only a tiny amount, almost unmeasurable, getting slightly bigger, and it's expanding, it's growing. And due to this, that sometimes pushes the railway sleepers over, and it bends the tracks and causes all sorts of problems, particularly in hot countries. You don't see it so much in the UK, but certainly in parts of India where there's and America where there's very long train tracks across very hot expanses, it does happen. Okay, so the word expand is the action of becoming larger or more extensive, and that happens in metals as they're heated up, and although they remain solids, their particles are moving around so much that it actually makes the metal slightly bigger. Okay, and this expansion can happen in gases and it can happen in liquids too. So they're still staying in the same state of matter, but the amount of it is growing just a tiny amount as the particles have got so much energy that they're jiggling around and taking up more space. The opposite to this is contracting. So I'm going to look at the word contracting here, and we've got here a thermometer, and this is one of the only metals that you'll really see as a liquid at room temperature. Okay, and this liquid it will expand and contract. It will grow, it will get bigger, and it will contract, get smaller very easily with changes of temperature. So what happens inside of a mercury thermometer, the metal's called mercury, what happens is as it gets warmer, it expands and it grows up the scale, and it indicates a warmer temperature. But when it gets colder, it contracts and makes itself smaller, and it manages to show us on the scale a lower temperature. So you can imagine if that liquid was growing, it would fill up more space and go right up the scale on that thermometer. Whereas when it's getting colder, it will travel down the thermometer to contract at the bottom there, the base of the thermometer. Okay, so that's how liquids can contract too. It's the process of becoming smaller. So that metal mercury expands to show a hotter temperature and contracts to show a smaller, a lower temperature. It takes up less space in the thermometer, so it shows a lower temperature. Okay, so this expanding and contracting without changing states of matter is actually quite useful in a few different ways, and we're going to look at those and explore those right now. So let's think, how can heating and cooling be helpful in these following examples? So example 1, putting a jar under a hot tap to help get the lid off. So you imagine you've got hold of a glass jar, it's got a metal lid on top. Already said metal contracts and expands quite a lot before it will melt or freeze. So if you've got a glass jar and it's got a really, really tight lid on it, how will it help to heat up that lid by running it under a hot tap? That hot tap is going to heat up the metal will expand, and if the metal expands, make it easier to twist the lid off the glass jar. It's an old way of opening glass jars. If they ever get stuck, you can try it. And if you've got a jar at home that needs opening, you can ask a parent if you can do that. Just be careful that the hot tap's not too hot, or whatever's inside it won't spoil because you're heating it up. Okay? But if you've got a jar that you cannot get that lid off, one of the tricks is to heat it up, make the metal lid expand, and it'll be easier to open. The next example is using liquid in a thermometer to tell the temperature. Okay, we kind of discussed this before, so have a think for a moment. Okay, the liquid in the thermometer, when it's heated, it will expand, and it will expand up the scale, and that will show a warmer temperature. Whereas if it's cold, the liquid will contract down the scale and it will show a lower temperature. It's a really accurate way of showing the different temperatures. What about cooling oxygen and hydrogen to put them into tanks? Now, oxygen and hydrogen are both examples of gases, so they'll be flying around everywhere. If you cool them down enough, if you get them cold enough that they bunch together, you can then put them inside tanks. It would be almost impossible to catch individual particles of oxygen and hydrogen to put them into a tank, and it would take forever. I'm not even sure there's a way. So if you cool down the temperature of the air, the oxygen will clump together, the hydrogen can clump together, and you can then put it inside of tanks. And once it's inside of tanks, you can use it. For example, the oxygen can be used used inside of breathing apparatus, so that you can go snorkeling or scuba diving underneath the surface of the ocean. Or if you need more oxygen because you're having an operation or you're poorly, then actually the oxygen tanks needs to have pure oxygen in them to be able to be used. Okay, so there's 3 different ways that this expanding and contracting can be helpful. Your job now is to pause the video and to complete my sentences about these 3 different helpful contracting and expanding scenarios. So number 1, heating the metal lid on a glass jar could be helpful because. Try and use the word expand or contract in each of these sentences. That first one, it'll be the metal lid expanding. And the second one, heating the liquid in a thermometer when you place it in something hot is helpful because. So think about when you put a thermometer into something hot, that liquid is going to expand. And what does that show you on the scale? So think about using the word expand in your explanation. And the last one, when storing gases like oxygen and hydrogen, cooling them is helpful because. Think about oxygen and hydrogen gas particles flying around, and how actually putting them closer together, contracting them, or even turning them into a liquid would help you to get them into a tank, and then what you can use that. So that one you'd need the word contract in that third statement. Okay, can you pause the video and complete those now? Excellent, good job. Our final part then, our reflection. How does the vibration of particles cause expansion and contraction? Could you draw a picture? Could you label a diagram? Could you write an explanation? Could you record yourself telling an explanation? However you would like to complete your reflection, please do so. And once you've completed your retrieval practice and your 3 statements on helpful contracting and expanding, plus your reflection, could you take a picture and put it onto Class Dojo, please? And I will see you next week's Science.